point f v in the plane and assigns each edge with the endpoints u v with a polygonal fu curve. The images of the vertices are distinct. The point in fe edges given, then we require a function f, which is nothing but a drawing of this particular function f. So f will map every point and when there is an edge between these 2 points, so f will draw a curve, polygonal curve. Now if there is a point while drawing the edges E and E prime, if there is intersection, if they are basically in the sense there is a drawing of this is E and this is E prime. So f of E and f of E prime intersection, if it is other than the endpoints, if there is a crossing which is not empty, then this common endpoint is called a crossing in this particular drawing. So it is common to use the same name for a graph G and a particular drawing of G referring to the points and curves in the drawing as the vertices and edges of G, since the endpoint relation between the points and the curves is the same as the incidence relation between the vertices and edges. The drawing can be viewed as a member of isomorphism class containing G. By moving edges slightly, we can ensure that no 3 edges have a common internal point, that an edge contains no vertex except its endpoints, and no 2 edges are tangent. So if 2 edges cross more than once, then modifying them as shown below, this can be redrawn so that they will not cross. Hence we consider only the drawings having these particular properties, that to our best we will consider the drawings without crossings. Definitions for a planar graphs and plane graph. A graph is planar if it has the drawings without crossings. Such a drawing is the planar embedding of a graph. So a plane graph is a particular planar embedding of a planar graph. So for example, if this is the graph which is called K4, here there is a edge crossing shown. Now we can redraw this particular graph using points and curves. So all 4 points will have, and this straight line or a curve we can draw. This particular edge we can draw from outside, as we have seen in the previous slide. So we have obtained a planar or a plane embedding of given graph K4. So this is called a plane graph. Why? Because we have obtained an embedding without edge crossings. So a plane graph is a particular planar embedding of a planar graph. So a curve is closed if its first and last points are the same. It is simple if it has no repeated points except possibly the first and last. Planar embedding of a graph cuts the plane into the pieces. These pieces are the fundamental objects of the study here in this topic. Definitions: open set, region, faces. Open set in the plane is a set in the 2-dimensional space such that for every point, all points within a small distance from P belongs to U. So the region is an open set U that contains a polygonal UV curve for every UV which contains in U. The faces of a plane graph are maximal regions of a plane that contains no point used in this embedding. So a finite plane graph G has one unbounded face, also called as outer face. The faces are pairwise disjoint. Points PQ in two-dimensional space lying in no edge of G are in the same face if and only if there is a polygonal PQ curve that crosses no edge. In the plane graph, every cycle is embedded as the simple closed curve. Some faces lie inside it, some outside. This again relies on the fact that a simple closed curve cuts the plane into two regions. As we have suggested, this is not too difficult for polygonal curves. We will present some detail of this case in order to explain how to compute whether a point is inside or outside. Dual graphs. A map on a plane or a sphere can be viewed as a plane graph in which the faces are the territories, the vertices are the places, and where the boundary meets. The edges are the portions of the boundary that join two vertices. So again, let us see that this is the map. So we can draw a map on a plane or a sphere. This is called a face. These are called faces. This is called face. It defines the territory of this particular region. The vertices are the places. We can define the boundary, let us say that comprises of the vertices are the places where these boundaries meets, and the edges are the portions of the boundary that joins the two vertices. So all these particular terms we will see. Now we allow the full generality of loops and multiple edges. So from any plane graph G we can form a related plane graph which is called its dual. So dual of a graph, which is denoted as G star, is a plane graph. G is also a plane graph whose vertices corresponds to the faces of G. As far as the edges of this dual graph corresponds to the edges of G as follows. If E is an edge of G with face X on one side and face Y on the other side, then the endpoints of the dual edge are the vertices X, Y of the dual graph that represents the faces X, Y of G. The order in the plane of the edge incident to X is the order of edges bounding the face X of G in a walk around its boundary. Let us see through an example. We can redraw another example, then I will explain it. For example, this is the graph G. What it says that if we draw a dual of this particular graph G prime, so it has the faces. This is face 1, this is face 2. So the faces of G represent the vertices whose vertices correspond to the faces of G. So the faces of G will become the vertices of G star. Let us say V1 and V2 are the vertices of as far as the edges of dual graph is concerned. We will draw the edges. If E is an edge, here this is an edge. If E is an edge with face X on one side and face Y on the other side, then the endpoints of the dual graph, the dual edge, are the vertices X and Y of G. So you see that V1 is a vertex on one face of G, and V2 is another vertex on another face of G, and there is a edge. So this edge we have to place between V1 and V2, which will cut through this particular length of this particular face, one side of a face. Now there is another side of a face and there is an edge, so we have to draw another edge around that and the third edge. So this particular red graph, again I will redraw G star, that is the dual, is nothing but V1, V2, it has a multiple edges and loops also. So this example shows it's a multiple edge. Loops will come whenever there is a cut edge. So every planar embedding of K4. So this is the K4 and we will see the this is the planar embedding. Or this is the plane graph of K4. Now we can see that there are 4 faces. This is region 1, region 2, region 3 and region 4. Has 4 faces and these pairwise share the boundary edges. So these boundary edges they share. Hence the dual is another copy of, if we draw the dual of this particular graph, so for every face there will be a vertex. So you see that there are 4 different vertices of a dual graph, and these boundaries, that means which are bounded by an edge in G, there will be also an edge which will connect those particular, so that is shown over here, dual graph. So every planar embedding of a cube similarly has, the cube has 8 vertices, 12 edges and 6 faces. The opposite faces have no common boundary. So the dual of this cube is a planar embedding of K2, 2, 2, which is a 6 vertices, which is having 6 vertices because it was having 6 faces, and 12 edges are common in both G and its dual, and 8 faces. Why? Because it has 8 vertices. Taking the dual can introduce the loops and multiple edges that we have seen. So if we draw a paw, this is a paw graph shown by the bold lines. So here it has 2 faces, 2 regions, 2 vertices will be there in the dual graph, and for every edge there will be a edge in the dual graph. So you can see that this cut edge will form a loop. Hence whatever we have discussed, that loops will be formed and multiple edges are also formed. So here this example shows the multiple edges, this is a loop and this is the multiple edges. In the dual of the paw graph. So the example shows that the simple plane graph may have loops and multiple edges in its dual. The cut edge of G becomes a loop in its dual graph because the faces on both the sides of it are the same. Multiple edges arise in the dual graph. Distinct faces of G have more than one common boundary edge. Some arguments require more careful geometric description of dual. For each face x of G, we place a dual of x in the interior. So each face of G contains one vertex and so on. So with this argument we can show that the dual of a graph, if we take the dual of it, that will be the original graph G. Hence dual of a dual of a particular graph is an isomorphic to a G graph. Now we can see that for the given 2 isomorphic graphs, if we take their duals, not necessarily they will be also dual. So this will be an example of a non-isomorphic dual. So here we have seen two different embeddings of a planar graphs, but if we take their dual, they may be non-isomorphic. So here we can see that so these particular graphs has three different faces. So in both the cases the dual has three vertices. So vertices, now in the embedding on the right side, the dual vertex corresponds to the outside face, has the degree 4. So this will have the degree 4. Why? Because this is one region, 1, 2, so we can see, we will see that it has the degree 4, but as far as this is concerned, this will not have degree 4. Here in this particular outside case, 1, then 2, then this will form 3, then this will form 4 and 5. It is more than more than 4, and here the dual will be of degree 4. This is 1, we will have 2, then 3 and then 4. So hence both are non-isomorphic duals. Why? Because here the degree is having 4 in this dual, and this is degree of more than 4, this is degree 4. So when a plane graph is connected, the boundary of each face is closed walk. When the graph is not connected, there are the faces whose boundary consists of more than one closed walk. How many edges are there? 6 edges are there. As far as its dual is concerned, so the number of vertices in the dual will be equal to the number of faces. So dual will have 3 faces, and as far as, so this is nothing but f of g. So edges are the same as E, that means 6 in this particular case, and the faces of a dual is the same as the number of vertices. So in the original graph, you know that the degree sum formula is applicable. That degree sum formula says that the sum of degrees of that particular graph is nothing but 2 times the edges of the graph. Now here we see that this particular edge E is same as E star, so that becomes 2 E star in that dual graph G. As far as the degree is concerned, here what we can do is that the degree is nothing but the sum of the lengths of the faces. So the sum of the lengths of the faces will become the degree. Hence this particular formula we have derived using degree sum formula. So let us see the proof. What it says, the face lengths are the degrees that we have already shown of the dual vertices. Since E of G is same as E of G star, so the statement 2 times number of edges that we have seen in the previous one, that is nothing but summation of the lengths of all the faces, is twice the number of degrees that we have seen. So this will be going to be equal to the degree sum formula, because E is same as the dual graph and the sum of the lengths of faces is nothing but the degrees of the dual graph. So proposition 6.1.13 illustrates that the statement about the connected graph becomes the statement about the dual graph. When we interchange the roles of the vertices and faces, the incident the edge incident to the vertex becomes the edge bounding a face, and vice versa. So the roles of face lengths and the vertex degrees interchange. We can also interpret the coloring of the dual graph in terms of G. So the edges of dual graph represent the shared boundaries between the faces of G. Hence the chromatic number of the dual graph equals the number of colors needed to properly color the faces of G. Since the dual of a connected graph is the original graph, this means that 4 colors will suffice to properly color the regions in every planar map, if and only if every planar graph has the chromatic number at most 4. So let us see the characterization of a planar graphs. So the following are equivalent for the plane graph, that is the G is bipartite. Second equivalence statement says that every face of G has even length. Third statement says that the dual graph G star is Eulerian. So A will derive A is equivalent to B. So A means G is bipartite, and this is equivalent to saying that every face of G has even length. Now let us see that the face boundary consists of the closed walks. So every closed walk contains an odd cycle. Therefore the bipartite plane graph, the contributions to the lengths of the faces are all even. Hence A is equivalent to B. Now B is equivalent to C. Let C be a cycle in G. Since G has no crossings, C is laid out as the simple closed curve. So F be the region bounded by the cycle C. Now every region of G is wholly within F or outside F. If we sum the face lengths for the regions inside F, we obtain the number, an even number, since each face has the length even. This sum counts each edge of C once. It also counts each edge inside F twice. Since each edge belongs twice to the faces in F, hence the parity of the lengths of C is the same as the parity of the full sum, which is even. Now B is equivalent to C. The dual graph is connected and its vertex degrees are the face lengths. Hence B is equivalent to C. Now we will see the definitions of a outer planar and outer plane graph. A graph is outer planar if it has an embedding with every vertex on its boundary of an unbounded face. An outer plane graph is such an embedding of an outer planar graph. Let us see in this particular example. So this is a planar embedding. Here we can see that all the vertices are lying on the outer boundary. Outer boundary means there is no vertices is inside this particular bounded region. Hence it is called a outer planar graph. Outer planar graph, and we have got this kind of embedding. This is called a outer plane graph. A particular embedding, if the graph has outer plane, the graph is outer planar if it has an embedding with every vertices on the boundary of an unbounded face, or a graph is called outer planar if it has an outer plane graph as an embedding. Proposition K4 and K23 are planar but not outer planar. We can see here in the figure that this is K4 and this is K23. So they are plane graph. Why? Because it follows this particular, it is a plane graph embedding, so it is a planar graphs, both are planar. Let us see whether it is a outer planar or not. We cannot obtain a outer plane embedding of this particular graph. Why? Because this particular vertex is inside, it cannot cross outside. If it cross outside, then these edges will cross, it will not be a planar. So there is no outer plane embedding of this particular planar graph, hence it is not an outer planar. Similarly the other one. To show that they are not outer planar, observe that they are two connected. Thus an outer plane embedding requires a spanning cycle. There is no spanning cycle in K23. There is no spanning cycle in K23, since it would be a spanning cycle of length 4, 5 in a bipartite graph. That will be length 5 is an odd cycle, hence K23 does not have any spanning cycle. However, there is a spanning cycle in K4y because there are 4 vertices. Now, if there is a spanning cycle, let us understand like this: it is having 4 cycle. Now this is a spanning cycle C4. Now here to complete this K4, let us assume that one chord will be inside K4. The endpoints of the remaining 2 edges, this particular edge, this alternate along this particular cycle. So the remaining cycle, but the endpoints of the remaining 2 edges alternate along it. So this is they will alternate. Hence these chords will conflict, cannot both be drawn inside. So drawing a chord outside separates a vertex from the outer face. So if this particular chord is drawn, then it becomes a planar, but separates a vertex from the outside face, because this will be creating a inner face. Hence this is not a outer plane. To show that they are not outer planar, observe that they are two connected. Thus an outer plane embedding requires a spanning cycle. There is no spanning cycle in K23, hence it would be a cycle of length 5 in a bipartite graph. Now there is a cycle in K4, this cycle is there, but the endpoints of the remaining 2 edges alternate along it. Hence the 2 chords conflict and cannot be drawn inside. Drawing of a chord outside separates the vertex from the outer face. Euler's formula: if the connected plane graph with n vertices, m edges and r regions, then n minus m plus r is equal to 2. This particular formula is well known as Euler's formula for plane graph. So it states for a connected plane graph having n vertices, m edges and r regions, then this particular formula will be satisfied that n minus m plus r is equal to 2. Let us take this particular example graph. This example graph has 7 vertices, 1, 2, 3, 4, 5, 6, 7. It has 9 different edges and 4 different regions, R1, R2 and so on up to 4. So n minus m plus 4 becomes 2, hence this particular equation is satisfied. Let us take another example graph. Here we have 7 different vertices, 8 different edges, 3 different regions which are shown R1, R2 and R3. If we plug into this particular formula, 7 minus 8 plus 3, that becomes 2, and hence it is satisfied. So it's not a coincidence, but for all such connected plane graph will satisfy this particular formula, and this particular formula is called Euler's formula. Let us see the proof by induction on the number of edges. Now for the base case, let us consider the number of edges as 0. So if there are no edge present, then it will be an isolated vertex, and that is nothing but a K1 graph. So in K1 graph, the number of node is 1, the number of edges is 0 and the number of region is 1. So let us include it in this particular formula. So 1 minus 0 plus 1, that becomes 2. Hence this particular formula is satisfied for the base case. Let us see the induction hypothesis. Suppose the theorem is true for all connected plane graphs with less than m edges, where m is greater than or equal to 1. So now we have to prove for the general case. Now consider a connected plane graph G on m edges, n vertices and r regions. There are 2 cases. Case 1 says that if G is a tree, now you know that a tree does not have any bounded region, the number of regions will become 1 for the tree, and if the tree has n nodes, it will be having n minus 1 different edges. So if we plug in to n minus m plus r the value of m, that is n minus 1, and also the number of region as 1, so this comes out to be 2. Hence if the graph is a tree, this particular formula is satisfied. Now let us say that if the graph is not a tree, then it has a cycle. Let us consider the cycle C, and on a particular cycle C there is an edge which is called E. Now if this edge E is not a cut edge, why? Because if an edge is on the cycle, then in the previous videos we have seen that it is not a cut edge. Hence E is not a cut edge. Hence if we remove E from a cycle, then the graph will still be connected. Hence G minus E is still connected and a planar as well, which has n vertices. Why? Because after an edge is removed, number of vertices will be intact to n values, n, and number of edges will be reduced by 1. How about the faces or the regions? Now we know that if we reduce an edge from a graph, the number of regions will also be reduced by 1. Take this particular example graph. In this example graph, if this edge is removed, then R2 and R3 will be in the same region. Hence the number of regions will be reduced by 1. So this graph will have, before removing the edge, it has 3 regions, and after the removing of this edge, the number of regions is reduced by 1, that will have 2 regions. So number of regions will be reduced by 1. Now by the induction hypothesis, this particular formula or the theorem holds for a smaller graph, that is G without T. Let us see that if, hence if we plug in these values over here, n as n and m as m minus 1 and r as r minus 1, so that becomes n minus m plus r is equal to 2. Hence this particular theorem is proved. Now there is a corollary which says that if G is a plane graph with C of G is the number of connected components, then this formula can also be generalized for the disconnected graphs, that is n minus m plus r is equal to 1 plus number of connected components in that particular graph G. Let us take this graph which is having 3 components, 1, 2 and 3 components. Now this particular graph has 1, 2, 3, 4, 5 different regions. It has 12 nodes and 13 edges. If we plug into this particular formula, so 12 minus 13 plus 5, that becomes plus 5, so that becomes 4. So 4 means 1 plus 3, so 3 is the number of connected components. So this particular formula is satisfied here in this particular example, hence this particular corollary is being taken into an account with the Euler's formula. So Euler's formula has many applications, particularly for simple graphs where all faces have the length at least 3. Let us use this particular remark as a theorem. So if G is a simple planar graph with at least 3 vertices, then E is less than or equal to 3n minus 6. Let us prove this. Now it suffices to consider the connected graph, otherwise we would add the edges. Euler's formula will reiterate n, will relate n and E if we can dispose of f. So the proposition which we have seen previously provides an equality between E and f. So again, if you recall, twice the number of edges is equal to the summation of lengths of the faces, that is given, that we have already seen. Now every face boundary in a simple graph contains at least 3 edges, that we have already taken. So therefore the number of nodes should be at least 3, so 3 or more. So that is basically the requirement for this particular theorem. So let Fi be the list of face lengths. So this will yield, if we take the sum of the faces, the degree sum or the proposition will give 2E is equal to sum of all faces, face lengths. So Fi's are all face lengths. Now you know that every face has length 3, that we basically 3 edges in a simple graph. So every face contains the length 3 and f is the total number of faces. So this particular formula, if we substitute for f, then it will 2E is greater than equal to 3f, then f is bounded by 2E by 3. If we substitute here n minus E plus so this becomes 3n minus E is greater than or equal to 6, so that becomes 3n minus 6 is greater than or equal to E, that we have proved. Now the another part of this particular theorem says that if G is triangle free, then the faces have the lengths at least 4, hence 2E is greater than 4 times f. So 2E by 4, that is f. So if we plug in this value, that is n minus E plus E by 2 is greater than or equal to 2. So 2n minus 2e plus e is greater than or equal to 4. This becomes minus e. So this becomes 2n minus 4. So e is less than or equal to 2n minus 4 that we have proved this particular theorem. Now we can prove the non-planarity of K5 and K33 using this particular theorem. Now for K5 we can see that total number of edges is 10. So if we plug in that particular 3n minus 6 is equal to, that is so e should be less than or equal to 3n minus 6. So here in K5 n is equal to 5. So that comes out to be 9. But how many edges are there here present? The number of edges are more. So it should be 9 or less than 9, since the number of edges are 10. So 10 is not less than, so it is basically greater than 10. So here the number of edges are more. So edges are more than 9 required for a graph to be a planar one. Hence it is non-planar. Similarly, E should be less than or equal to 2n minus 4, and here in K33 we have n is equal to 6. So that comes out to be 8. So E should be less than or equal to 8, but the total number of edges present is 9. So here also the edges are more than 8 to be planar. Hence this is a non-planar graph according to the Euler's theorem. Now the maximum planar graphs and triangulation. A maximal planar graph is a simple planar graph that is not a spanning subgraph of another planar graph. A triangulation is a simple plane graph where every face boundary is a 3 cycle. Now there is a proposition which will make 3 different statements which are equivalent. So for a simple n vertex graph, the following are equivalent. G has 3n minus 6 edges, G is a triangulation, and G is a maximal plane graph. A is equivalent to B. Now for a simple n vertex plane graph, the proof of the theorem shows that the graph is having 3n minus 6 edges is equivalent to saying that 2e is equal to 3f that we have seen in the previous proof of the theorem. So which occurs if and only if every face is a 3 cycle, and that is nothing